Welcome to Public Health on Call, a podcast from the Johns Hopkins Bloomberg School of Public Health. I'm Joshua Sharfstein, Vice Dean for Public Health Practice and Community Engagement, and a former health commissioner here in Baltimore. Our goal is to bring evidence and experience to illuminate critical public health issues. If you have questions or ideas for us, please send an email to publichealthquestion@jhu.edu. That's publichealthquestion@jhu.edu for future podcast episodes.
Hi, I'm Lindsay Smith-Rogers, producer of Public Health on Call. Today, Dr. Andrew Pekos, a virologist and professor at Johns Hopkins, returns to the podcast to talk with Dr. Josh Sharfstein about all these variants, what they mean, and how we can protect ourselves. Let's listen.
Dr. Pekos, it's good to see you this morning, and thanks for coming to Public Health on Call.
Great to be on, as always.
So today we're going to talk about the COVID variants, and to make it pretty simple for me, you sent me a graphic. I'm joking because the graphic is so complicated, and I think this graphic looks like it has a very confusing, detailed lineage of about 100 or so variants just of BA1 and BA2.
Absolutely. And throw in a little bit of BA5 because here in the US in particular, that has been the virus variant that has been dominating here. And you've got a real sort of absolute mess in terms of trying to keep track of which viruses are coming from where, and importantly, what mutations they're carrying.
So just to take a step back, I had kind of figured that there were going to be Greek letters for the major variants, but we have sort of gone afield from that plan. What happened?
Well, the Greek letter idea was a great idea for simplifying things. But what Omicron has sort of shown us is we started with 4 different lineages that were called Omicron. They were all slightly different. Each of those has continued to circulate and accumulate mutations. In the past, when one variant has emerged, it's really become dominant globally. And so we haven't had this situation with SARS-CoV-2 where we had 4 lineages starting off, each of which have now mutated into sublineages. And as you see from some of the graphics here, it just becomes then a nightmare in terms of keeping track of everything because no one is out competing the other. They're all around at low levels. And more importantly, even, they're all sort of accumulating now the same types of mutations that are of really high concern to us virologists.
So there basically weren't enough Greek letters.
And if we were using Greek letters, we would probably be into the Latin alphabet by this point in time to try to keep track of some of these variants.
So let's talk about this point that you just made, that you have dozens, scores of variants, but they are separately evolving similar characteristics. Well, what are those characteristics and what do they mean?
Yeah, so out of all of these different lineages, it seems to be that there's a couple of common themes that are coming through. Not to get too detailed, but amino acids 346 and 440 are 2 examples of how each of these separate lineages has independently picked up those mutations. And why are those mutations important? They knock out very clearly evident epitopes that are targeted by the vaccine, and they knock out epitopes that are also targeted by monoclonal antibody treatments, which a lot of immunocompromised people take because they don't have very good responses to the vaccine. So this is an example of what we call convergent evolution. All of these Omicrons sort of mutated and moved off in lots of different directions, but now they're all coming together on one set of common mutations that seems to be advantageous to all of them, despite the fact that they look so different from each other right now.
Let's talk about the clinical impact of those. For the monoclonal antibodies, do these mutations really totally evade the antibody? You don't get much protection from them if you happen to run across one of these variants?
Yeah, Omicron came in already losing a few of the monoclonal antibody epitopes, and these last 2 mutations that have come up have pretty much eliminated every single monoclonal antibody that's on the market right now in terms of their efficacy. It's been interesting to see that there hasn't been a real push for a second generation of these monoclonal antibody therapies because honestly, it should be straightforward to come up with a second generation set of antibody therapies that target Omicron. It just doesn't seem to be something that is on the horizon in terms of replacing those first generation monoclonal antibody treatments.
I mean, the issue, just to be clear, is the mono part of monoclonal. So these monoclonals are one tiny type of antibody, one specific type of antibody. And as soon as there's a mutation to get around it, you basically are sending in a whole lot of the same thing, and all of them fail.
Yeah, a couple of companies have tried to put two together, and that works to some extent. But again, after a while, given all of the lineages and all the mutations that Omicron is picking up, it's just a matter of time before they fail. And again, that second generation of let's find a replacement that recognizes the new variants hasn't come down the pipeline clinically.
Right. Well, that's not good news for people who are relying on those to stay healthy because they don't have a vaccine response.
Absolutely. And we know here at Johns Hopkins, there's a group of individuals, solid organ transplant recipients, to be precise, that really do rely on these monoclonal antibodies as their means of protection because they really have no other way out. Oftentimes, they're not eligible to take the antiviral drug Paxlovid because of drug interactions. So they really rely on these monoclonal antibody treatments to provide them protection from COVID-19.
Well, let's talk about vaccines and see if there's any better news there. I know that the vaccine response is not monoclonal, that when you get a vaccine, your body makes many different types of antibodies. So does that make it harder for these variants to evolve completely around vaccine protection?
It absolutely does. And the fact that we've moved now to this bivalent COVID-19 vaccine that actually has the original vaccine plus an Omicron spike protein in it as well has really helped move the vaccine to be much more specific to the viruses that are circulating right now. Now, again, viruses do what viruses do, and they're picking up some of these mutations to evade that immunity. But because the vaccine induces this polyclonal response, we're seeing stronger protection against severe disease with the bivalent vaccine, despite these mutations coming up.
So of all of this alphabet soup, there's no basic change to the recommendation to get vaccinated.
Absolutely not. If anything, it's been surprising to me how low the uptake has been for the bivalent vaccine, because this really represents an updating that could have gotten us far ahead of the virus. But as with most interventions at the public health level, right, unless we get good buy-in and utility in terms of getting it into the population to a high extent, it's not going to serve the purpose that it really was initially supposed to serve.
So what do you think the future is for all these variants with such intense and frequent mutation? Are we just going to be tracking this and looking at the same things, whether or not the monoclonals might work, how we're doing with vaccines, looking at the outcomes for people who've been vaccinated with different products? Are we just in this for the time being, or what do you see happening?
Well, we certainly have to realize that we now have tools. So we have vaccines, we have testing, we have antivirals, right? All of these things keep down the severe disease with COVID-19, and it also keeps down, to some degree, infections and transmission. We have to keep these tools up to date and ready to go. They're the swords that we use. We have to keep them sharpened and keep them really specific to the viruses that are around. It's analogous to what we do with influenza. We try to keep track of the virus and update our vaccines and our treatment regimens based on what the viruses are circulating. The problem with SARS, though, is it's mutating and evolving at a much, much faster rate than a virus like influenza is.
I've always wondered this. Is there a risk that tests might stop working and the tests would have to be changed to keep track with the virus, or are you not worried about that?
It's a great question. There always is a risk. And we and other laboratories are always providing the rapid antigen test companies with new variants so they can go into the laboratory and actually test their kits for reactivity against these variants. So it's something that's on everybody's radar screen. Many of the companies know exactly the sequences that their tests recognize in the virus. So they can almost tell from a sequence whether or not these things might be, these new variants might be a problem for their detection kits, and they go out and then they test them against them.
So you really got to check the antigens. What about for PCR testing, where they are looking for very specific genetic sequences? Is the variability in the virus affecting the areas that the PCR tests are looking for?
Yeah, those have been fortunate. For the most part, they've tried to target regions of the genome where historically coronaviruses haven't mutated much. And many of those PCR primers still continue to recognize variants. We've had a few examples of tests that haven't worked that then get updated. But for the most part, the PCR-based tests are holding firm. But again, the companies are really looking at those sequences and are ready to update if anything would emerge that might interfere with their sensitivity of detection.
Got it. I want to just take one final big step back. The beginning of this pandemic, I was hearing that we didn't think that coronavirus has mutated quite as much as flu. Now you're saying this is mutating much faster than flu. Is this something we've learned about coronaviruses because we're just looking so carefully? Or is this particular virus truly different than the others? Does it have to do with the scale of the number of people who've been infected? What do you think is going on?
Yeah, I think the scale of this pandemic is certainly one of the factors that probably hasn't occurred with any of the other coronaviruses that have jumped from animals to humans. I think we also have never really been able to track a coronavirus's entry into the human population as well as we've been doing with this one. So we're seeing a lot of the details of what the virus has to do to optimize itself to replicate in humans. And so, again, this is real-time evolution here that we've been watching that we've never had a chance to track before. And so it's hard for us to draw the comparisons to when other coronaviruses first entered the population.
Maybe we miscalculated because we essentially were relying on past experience where we didn't have that bright a light. But during COVID, such a bright light on what this virus is doing, we now understand that the mutation and these variants are really what the virus does.
Yeah, absolutely. And I think the big question right now, if we're going to step back, is, many of us in the virology field have been waiting for this virus to start to show a seasonality, right? We assumed it would peak in the winters. We assumed it would go away in the summers. We haven't seen that seasonality yet. If anything, we're settling in at a steadier number of cases almost year round. And so that's really the thing that we're trying to pay attention to now is, will this virus go seasonal? Because that makes it a little bit more easier for us to vaccinate and come up with strategies to contain it. If it's a threat that's going to be here year round, then we really have to keep our guard up and probably update vaccines and therapies and those kind of things at a much faster rate.
And does the seasonality issue relate to the underlying variation in the virus? In other words, do you get seasonality when there's more stability in the virus and more stability in the human response to it? And because we haven't had that stability, we don't have seasonality? Are those two things related?
Yeah, that's one of the hypotheses that we've always had about these respiratory viruses that circulate only in the winter. It's this combination of population immunity and the inability of the virus to mutate very quickly. That means that it spreads in ideal situations, the winter when you're indoors in close contact, and then in less than ideal situations like the summer, you don't see the virus spreading as well because it can't do it into those situations. Again, we haven't seen that transition come through yet with SARS-CoV-2, and that's what people are really, really interested in trying to understand, whether that will happen or whether we'll be dealing with this on a monthly basis.
So interesting, Dr. Pecos. Thanks for all you are doing, keeping your eye closely on this virus. And thanks for coming back to Public Health on Call.
My pleasure.
Public Health on Call is produced by Joshua Sharfstein, Lindsay Smith Rogers, and Stephanie Desmond. Audio production by J.B. Arbogast, Holly Cardinell, Spencer Greer, and Matthew Martin, with support from Chip Hickey. Distribution by Nick Moran. Production support from Catherine Ricardo. Social media run by Grace Holes Fernandez and Amber Bryan Singletary. Thank you for listening.